Hello everyone, today we're going to be talking about Stoichiometry, the Wunderfractions. Yeah, we come back to the Wunderfractions. I know you have missed doing the Wunderfractions, so we are back again. But today once again, we're going to be doing solution stoichiometry. This should be largely review here for most of you, so hopefully you remember how to do your lovely Wunderfractions. Stoichiometry again is just that process that we've gone through a bunch of times before, where we're using multimole ratios from a balanced chemical equation, and we're using it to be able to predict either the amount of reactants that we need or the amount of product that we're going to make in a given chemical reaction. So this exact same thing is what we've done earlier this semester, where we started off with a mass of a particular reactant, and then we tried to figure out how much product we were going to make. We had to balance the chemical equation, we did a little wonder fraction, and then we calculated whatever it was that we needed. So same basic idea is here. This is simply going to be dealing with solutions. So rather than dealing with masses, a lot of times we're dealing with molarities instead. Same idea. So here we go. This particular video, part one here, is mostly one big practice problem. So if you don't have a calculator or a periodic table, you should probably think about getting one. But anyway, there's part two of this, goes into a little bit more detail, like the limiting reactants problems and all that stuff. So let's dig in here. So here is a good example of a review of how to do these problems, just in case. If you really remember how to do this, you're really comfortable, fine, fast forward. But here you go. So practice problem, how much carbon dioxide would you need to create 12.8 grams of glucose through the process of photosynthesis? So if you remember way back when to January, how did we solve these problems? So number one, we had to write a balanced equation. You have to know what glucose is, what photosynthesis is, and all that stuff. Number two, we had to convert from grams of something, like glucose, to the moles of that thing. Then we had to use the balanced equation to convert from moles of one thing to moles of the other thing. So we converted from, in this case, moles of glucose to moles of carbon dioxide. And then the last process was to convert those moles of our product back to grams using molar mass. So let's take a look at how this works. So here it is. If you want to, practice, work it out, hit pause before you look too far, but this is what the product would look like. So here's our chemical equation for photosynthesis. 6CO2 plus 6H2O yields C6H12O6 plus 6O2. So there you go. There's our balanced equation. Remember, it has to be balanced in order to do these. And then we started off with whatever was given to us. So over in this first step right here, we've got what was given in the problem. Our 12.8 grams of glucose is what we had. Then we used molar mass is the second step. Molar mass is 180 grams. That's 6 carbons plus 12 hydrogens plus 6 oxygens. So 6 times 12 plus 12 times 1 plus 6 times 16. And that's 180. And that gives us 1 mole. So remember, grams is on the top, so grams is on the bottom. We've got to get those to cancel out. Then the next step, here's our stoichiometry step. We're going to use the coefficients from that balanced equation to convert from moles of one thing to moles of the other thing. So we're converting from moles of glucose to moles of carbon dioxide. And again, there's a 1 here, and then there's a 6 there. So that's why we have where these two values came from. 1 mole of C6H12O6 produces or yields 6 moles of CO2. And then the last step that we have to do is convert back from moles to grams. So moles is on the top, moles is on the bottom. Crosses down, and then this is the molar mass. 44 grams is the molar mass of carbon dioxide. That's 1 carbon, which is 12 grams, and 2 oxygens, which are 16 grams each. So by the time you do all this out, remember, you multiply across the top, so it's 12 times 1 times 6 times 44, and then you divide by everything on the bottom. So we're dividing by 180, divide by 1, divide by 1. We get our final value of 18.8 grams in 3 sig figs. So hopefully remember how that works. If not, hit pause right now and stop immediately, and we can come talk this over in class, because I'm moving on from here. So here it is with stoichiometry, with solutions. A little bit different. So let's take a look at what it is. In this case, we're still going to use the balanced equation. Got to have that. We're still going to use the multimole ratio. Got to have that. But typically in these kinds of problems, we don't start with grams of a reactant or grams of a product. We're starting with molarity. We're starting with a solution of some sort. So we're going to have to use that molarity equation. So here's our problem-solving strategy. Number one, you got to write that balanced equation. You've got to use the molarity equation, right? Molarity equals moles per liter to calculate how many moles of A we've got. Once we've got moles of A, whatever A is, we're going to use that balanced equation, that stoichiometry step, to convert from A to B. And then that last step, we're going to convert moles of B to whatever it is that we need. Sometimes it's grams of a product. Sometimes it might be, we might use that moles of B in a second molarity equation and figure out what's our new solution concentration. Just kind of depends on what the problem is. So take a look at the problem to figure out what you do for step number 4. So these next few slides are going to work through kind of in detail one of these problems. So again, you need probably a pencil, piece of paper. You might want to get your calculator out at this point. So let's take a look at working out a problem. Here we go. How many milliliters of 0.1 molar lead-2 nitrate solution are required to precipitate all the lead in the form of lead-2 iodide from 125 milliliters of 0.1 molar NaI, sodium iodide solution? Whew. First thing first, got to figure out what the hell that's actually saying, right? Decode the problem. What are the chemicals that we're dealing with, and what are we getting when we're done? So we're reacting two things together, lead-2 nitrate and sodium iodide. Those are the two things that we're reacting together. Those are our reactants. So you can see I've got them written down here. Lead-2 nitrate. Again, why is it lead-2? Well, that's where this little 2 comes from. Remember, nitrate is a 1 minus. Lead is a 2 plus. That's what lead-2 means. Sodium iodide, NaI, is our second one, and that was actually nice enough to give you the formula there. What are our two products? Well, one of our products is lead-2 iodide. Lead-2 iodide is one of our products. The other product you have to figure out here is lead-2 iodide, but you can figure that out because this is a double displacement reaction, so you'll know that the other product has to be the other two ions, which are sodium and nitrate, so that would form that. Lead-2 iodide, again, the formula for this is PbI2. Remember the I2 here becomes because lead-2 is 2 plus. Iodine's a 1 minus, so that's where that little 2 comes from. Sodium and nitrate are our 2. Sodium's a 1 plus. Nitrate's our other is a 1 minus, so those guys bond together in a 1-to-1 ratio. And then the last thing is I balance the equation. Because I've got 2 nitrates on this side, I need to have 2 nitrates on this side, so that's where this 2 came from. As soon as I have a 2 there, I have to put a 2 in front of the sodium iodide, and then everything balances out all happy. So I have 1 lead, 2 nitrates, 2 sodiums, 2 iodines on the left, and on the right I have 1 lead, 2 iodines, 2 sodiums, and then 2 nitrates on the right. So hopefully that makes sense to you in terms of how to balance that equation. If not, again, hit pause, run, come see me in class, we can talk about where that is. The second thing I do, and I always do this when I solve these problems, is I label what's what. So I'm trying to figure out how much, what my volume of lead-2 nitrate is. I know it's a 0.1 molar solution because that's given to me in the problem. And then I label underneath the other solution what I have. I know I've got 125 milliliters of 0.1 molar NaI solution. So again, when I write these out, I write them directly underneath because sometimes they're two products. It might be a product and a reactant. But that way it helps me kind of keep track of what my numbers are. Okay, let's move forward to the next step. Next step is calculate the moles of whatever that we've got. In this case, our known is sodium iodide, so that's where I'm going to focus. This is my unknown. This is my moles of B. I don't know what I've got yet. My moles of A, though, is what I'm going to deal with. So I'm going to use the molarity equation because I've got all the pieces I need for that, and try to figure out how many moles of sodium iodide I have. Again, here's our molarity equation, moles per liter. Remember, this is in milliliters, so I have to convert that to liters first, move the decimal place over 3, and that's where this comes from. I have 0.125 liters of that solution. Again, it's got to be in liters. This is my known for my problem, 0.10. So just rearrange. I know I've got 0.0125 moles of my A, which is sodium iodide. Next step. Next step is I'm going to convert from moles of A to moles of B. This is the stoichiometry step. This is where you need to do a Wunderfraction, yeah. So here's where I got my answer for my last step. I had 0.0125 moles of A, and then here is my stoichiometry step. Where did those numbers come from? They come from the balanced equation. I've got one of these is going to react with 2 of those. So I've got 2 moles on the bottom. Why is this on the bottom? Because it was on the top in the previous steps. Remember, crosses down. So I've got 1 mole of this is going to be produced up on the top. So I know I'm going to get 0.00625 moles of lead-2 nitrate produced. Now our last step. We've got to convert our moles of B to whatever we need. So what do we need in this case? Well, we don't need mass, we need milliliters. That's what we're trying to find. So we're going to focus in on this. If I don't need mass, I'm not going to do Wonder fraction. I need volume. Volume means I'm going to use the molarity equation. Again, here's our molarity equation. It comes back to haunt us like all the time in this chapter. So what have I got? Well, I know this, 0.10 molar, because that was what was given to me in the problem, is going to be moles of B over liters. And I'm looking for volume, so that's good. Well, here's my moles of B. Where did I get that from? That's the answer from the previous step. Remember, we got that from the stoichiometry step. So now, this is the part that's going to screw you guys up. I'm looking at you. Yeah, you. You know who I'm talking to. This is the algebra that screws everybody up. Please do this slowly. I guarantee you more than half of you are going to solve this equation wrong. I'm not sure why. It happens all the time. So please, 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 please be very careful when you do that. Take a look at how I've got this set up. When you move this, you multiply both sides by liters. Liters are on the top. Divide both sides by molar to get molar on the bottom. That's where this comes from. Double check it. Please go so. Please, please, please. So your final answer is, when you do the math, 0.0625 liters, also known as 62.5 milliliters. And there you go. So, in terms of doing the stoichiometry, here's our basic review. You always know these are basic stoic problems because quantity of one chemical is given, and you're asked to find the quantity of a second one. These are the simpler ones. We're going to do limiting reactant ones in the second video. But in any case, you may be solving for grams, you may be solving for milliliters, but these are stoichiometry problems. You're converting from one chemical to another chemical. This is not dilution. Dilution problems are when you have one chemical and you're making a solution of the same chemical. Stoichiometry is one chemical converting to a different chemical, and that's a key point so that you use the right problem-solving strategy. When you're doing this, again, your strategy is down below. You're going to write your balanced equation. You need to know what that ratio is. You're going to use the molarity equation typically to find how many moles of A. You might be using a grams to moles equation, but something, you got to find moles of A. You're going to do that stoichiometry step to convert from moles of A to moles of B. And then your last step is you're going to convert your moles of B to whatever. Could be in grams using molar mass, or it could be in milliliters using your molarity equation. So there you have it. Part 2, we'll take a look at the slightly harder versions of this. I'd suggest you hit stop, go practice a problem or two, and I'll see you in class tomorrow.